All right, Dave again here with another question bank question on superposition and interference and the speed of sound. We have an experiment to measure the speed of sound. Two coherent sources, S1 and S2, produce sound waves with a frequency of 1700 hertz. They're coherent, meaning that they're fed by the same source of sound, the same waveform generator, so the sound coming out of S1 and S2 is going to be doing the same things at the same time. Now, a sound detector is moved along the line AB, parallel to the line S1, S2. When the detector is at P, such that the distance from S1 to P is equal to the distance from S2 to P, we get a maximum loudness at P. As the detector is moved along the line A to B, regions of minimum and maximum loudness are detected, and as we move from P to X, point X becomes the third position of minimum loudness from P. The difference in the distance between S2 and X and S1 and X is half a meter. That's the path difference. We want to use this information to determine the speed of sound. All right, let's zoom in here a little bit. We said that point P was a maximum loudness. It's also the point where the distances between S1 and S2 and point P are equal. That means that the path difference at P is 0. So the difference in path between S1 and P and S2 and P is nothing. That means they wind up doing the same thing at the same time at P, the waves do, which means that we get a maximum loudness. Now, as we move away, though, there's going to become a path difference will emerge, and at some point, the path difference will become half a wavelength. This will be the first point at which we get a minimum loudness. We'll continue on, and sooner or later the path difference will be a whole wavelength. That's another maximum. Eventually it will become 1.5 wavelengths. That's going to be the second minimum. We'll continue on to 2 wavelengths, and finally we'll reach X, where we expect that the path difference will be 2.5 wavelengths, becoming the third point where we reach a minimum in intensity. So we know that the path difference between the path from S1 to X and S2 to X has to be 2.5 wavelengths. We also know from the question that that path difference is half a meter. So we get to say that the path difference at X is 2.5 wavelengths, and it's equal to 0.5 meters. Turning this around and solving for wavelength, we get 0.50 on 2.5, or 0.20 meters. And that's the wavelength of the sound. We wanted the speed of sound, though, so we have to turn to this relationship. Wave speed equals wavelength times frequency. We just determined that the wavelength was 0.20 meters. And the question told us at the beginning that the frequency of the sound is 1700 hertz. Multiplying these two together, we get 340 meter hertz. But hertz are per second, so this is 340 meters per second.